It's nice to present Yorck Sommerhäuser from the Memorial University of Newfoundland, who will talk about new examples of semi-simple Hopf algebras. Thank you.
Yes, thank you very much for having me. And as it says on the slide, this is all joint work with Evgenia Kashina. And so let me give you some references, mainly to her work, in fact. So most of you will know her classification of semi-simple Hopf algebras of dimension 16, which will come up in a while. But there are actually two consecutive papers to this. This is the first one, and this is the second one, where she kind of describes Hopf algebras of dimension 2 to the power m, which arise from similar constructions, so to speak. How does this generalize? And then there are two new papers of ours just out. They were submitted to the ARC. They now appear more or less simultaneously, but they were not written simultaneously. The reference 4 is 1 year older than or was at least posted to the archive 1 year before the second one, but now they are both out. Okay, so let me briefly give you an overview. Some of you, this is actually some of you have heard me on this on various occasions, in particular, some of you in Mexico City, one of the last talks that I gave before the Corona crisis. So we will start to discuss here the Drinfeld Hopf algebras of dimension 8, and then we will discuss their byproducts, which have dimension 32. We will try to realize these byproducts as extensions. And then I will finally discuss self-duality and isomorphisms of these Hopf algebras. So this is the first, there will be two examples for this here, the Drinfeld Hopf algebras that I come up with. So we need a fourth root of unity, fourth root of unity where iota is required primitive, but zeta is, iota is just my notation for I in the field. But zeta is really the decisive thing, and which enters into the definition as you see here now. So the Drinfeld Hopf algebra is generated by two commuting elements x and y, which are subject to the following defining relations. So first of all, the fourth power of x is equal to 1, and the square of y is equal to this relatively complicated expression in x, which involves zeta but not iota. And so I introduced two automorphisms of this algebra. Namely, first of all, it's defined on generators by mapping the first generator to x cubed and the second generator to x cubed y. And you can check that these satisfy these relations too. It's a little computation. And then the second automorphism is leaves x fixed and moves y to x squared y. This Hopf algebra has dimension, yet the Drinfeld Hopf algebra has dimension 8, as you may already guess. And the basis is given like this. So it contains 4 elements denoted by omega with corresponding indices, and 4 elements denoted by eta. And from these, how are they defined? Well, omega 1 is just 1. And then here, omega 2 and omega 3 are just linear combinations of the powers of x. Here you see the x and x cubed. Here you see 1 and x squared. And because of the defining relation you conjecture, this is exactly the span, a different basis of the space spanned by the x's. And here it's simpler. So for the etas are just y times the corresponding powers of the x's, enumerated a little bit strangely. Why do I introduce this basis? By the way, one comment, the iota shows up only in, here you see the iota in 4 places. It shows up only in this transition matrix from one basis to the other. So in a certain sense, you can define A without using iota. And so what is the core? So this is the algebra structure. The core algebra structure is determined by requiring that these basis elements, which I've just introduced, the omegas and the etas, are group-like. So this means that these two equations here are satisfied. But this is supposed to be a yet Drinfeld Hopf algebra, which is not an ordinary Hopf algebra, as I explained on many occasions, so that most of you guys are familiar with this, I guess. And so it is again Drinfeld-Hopf algebra over the group ring of a group, and the group is just Z2 times Z2, where the group elements in the sequel will be denoted like the unit element is G1, the two canonical basis elements are G2 and G3, and their sum is just G4. So it's the Klein 4 group. And of course, it's generated by G2 and G3, and G2 acts by this automorphism phi that I've introduced before, and G3 acts by this other automorphism, which I've also introduced, which was denoted by phi prime. And under this action, it turns out that the etas form 1G orbit, whereas the omegas are moved by phi, but not under omega 1 and omega 1 and omega 4 are fixed point under the entire action. So this is the orbit structure, and I won't go into this today, but in Mexico City I explained, and this was the purpose of these Drinfeld-Hopf algebras to begin with. There is a notion of a core of a group-like element, and in the prime order case, it turns out that these are always completely trivial in the sense that both action and co-action are completely trivial. The omegas here form such a core, and you see there's a non-trivial G orbit being here. So this core is not completely trivial. However, it is trivial in a sense, but I discussed this in Mexico City. I will discuss something else today. So to get the Drinfeld-Hopf algebra, you need a coaction 2, and the coaction looks as follows. They are not only fixed points, also invariant, but also co-invariant. This means that the coaction is given by these two formulas, and for the other ones, it's more complicated. Otherwise, we have that the coaction on these is this linear combination, and on omega 3 it is given as this linear combination, which only differ by a sign here. There's otherwise no difference. So this describes it for the omegas, and for the etas, it's a little bit more complicated to describe it, but some of you know that you can get a Drinfeld-Hopf algebra from module Hopf algebra if you have an R matrix, and this is happening here, although I'm hiding this fact from you. So there's an R matrix in the background, but for the etas, it is necessary to use this to go closer to this U point. So you define on this Klein 4 group, you define a symmetric bilinear bicharacter, I should say. It would be more appropriate if I take values over here, by requiring that the fundamental matrix, so here is, you see the values on the canonical basis vectors, which of course determine the bicharacter, is given by this matrix. And here you can basically choose whatever you want as long as you have these elements of order 2. And then you define the coaction as follows. So you see here the coaction on eta k is, this here is in H, and this here is again in A. Oh, that was not right. So it's a double sum, and here these elements are numbers. These are coming from this bicharacter or bilinear form, which is defined over here. So this is how the coaction looks. There's also an antipode, which I flash very briefly. So the omegas are all inverses of themselves, but here you see it for the etas. In the Drinfeld-Hopf algebra setting, I explained this also in Mexico. It is usually not the case that the value of the antipode on a group-like element, which is the inverse of this group-like element, but it's usually not again group-like. As you see here, it's not it's a linear combination of 4 different group-like elements, so it's not group-like itself. And then the other ones have a similar form. You can compute them from here. You don't have to memorize this, guys. I will not put it on the exam. Okay. Yeah. Yeah. Okay. So there's a second example, which is non-commutative, denoted here by A prime. So it's generated by 2 non-commuting elements, x and y, subject to very similar relations. X to the 4 is 1, y squared is an expression in y. But you see here the middle relation is now new. So x and y don't commute anymore. Rather, they commute up to xy is yx cubed. There's this cube now. Yeah, so so it's not commutative. The other structures I won't describe in detail. They are very similar to the first example. So, and this is the focus in this talk today. So you, for each yet Drinfeld Hopf algebra, you can form a so-called Redford byproduct. I know that the Argentinians like to call this the bosonization, which sounds much fancier. Um, so it's modeled under the underlying vector space is A tensor H, and the multiplication is, and you have seen me many times do this if you have attended a couple of my talks. So and usually somebody's in the audience, so I get to some person and kick somebody, right? You have seen this a couple of times, I guess. But here I can't do this because we are not in the same room altogether. But while this guy H here passes this A prime, he misbehaves, and with his left leg, he kicks this A prime. This is how this multiplication works, yeah? Very aggressive, yeah? And the co-multiplication is different. Here we have something which I call the co-kick, yeah? Here, so here we have a kick, and Peter Schaunburg always asks me to perform this live on stage, so to speak. Here you have this additional term, the co-kick, yeah, from it's not A1, A2, it's A1, 1, this is the co-action, A2, 2. So this is an A, this is an H. It's a little contrary to what the other notation uses. So you can, this is the general construction. You can in particular plug it into the first example. If you've carried out as the underlying vector space is the tensor product, the dimension is dimension of A, which was 8, times dimension of H, which is 4. And most people don't need this computation. So 4 times 8 is 32. So of course you can you can then get generators. The ones from A, coming from A, and the ones that generate the group, these are called R and S here. And it's from the presentation of A that I gave, it is not very difficult to derive a presentation of B. So these are the same relations that I had. These are those that come directly from X and Y, the analog of what was there before for A. Then here we have the relations that encode that we are in the Klein 4 group. So we have 2 elements of order 2 which commute. And then are the relations that encode that we're in a Redford byproduct. This is this kick action that we, how these elements commute. So, and it's very easy to see that this is the presentation in terms of generators and relations. Then you can also work out the co-product from the co-kick formula that I did before. And of course, in this formula, you see that the group-like elements stay group-like. It's not, the details are not important here, but you can work out the co-products for the other generators. And this is how they look. U is still civilized, and V is a little bit messy. But again, this will not be on the exam, so you don't have to memorize this completely. You can work it out, okay? So what is the Vedderman decomposition of all this? It's a semi-simple Hopf algebra. I should say we have assumed in the second paper that we are working over an algebraically closed field of characteristics 0. So this is an assumption here. I a little bit regret this because we could have been a little bit more accurate with that. But under these assumptions, so B is semi-simple, and how does the Vedderman decomposition look? So it's a direct product of matrix rings. 8 of 1 are just 1 times 1 matrices. 2 of them are 2 times 2 matrices, and one block is 4 times 4. Okay, so this is how the Vedderman decomposition looks. And now I've constructed this B of dimension 32 as a Redford byproduct. And the usual way, and this is how Jeannie and I started discussing this, she said, well, this is all obvious. This is like in my constructions, the 3 references that I gave you before. All this is an extension of the following kind. And then we work through this. And the main message of today is this is not so, okay? Yeah. So this is these Hopf algebras are exotic from her perspective. So the Hopf algebras that she had already in the three initial references that I showed you do not cover these. So, so as I said, very frequently and more frequently, semi-simple Hopf algebras are constructed as Hopf algebra extensions. And this also holds for B. B can also be constructed via extensions and in four ways. And I will now read you how this can be done, but also I will tell you how what the difference is in comparison to Genia's previous work. So first of all, B contains a unique 16-dimensional Hopf algebra N. A unique 16-dimensional Hopf algebra N. This is normal, and it's item. I told in reference one, Genia's classification of the dimension 16 Hopf algebras. It's dimension the Hopf algebra HD11 from her list in her dimension 16 classification. So this means in particular, this is neither a group algebra nor a dual group algebra. But because this is normal, B can be constructed as an extension of the following type. B is in the middle, N is this Hopf algebra, and the quotient is, of course, two-dimensional then. So dimension N is 16, and the quotient must be two-dimensional. This extension is obviously not abelian. So this extension here is not an abelian extension. We can construct it as an abelian extension, which I will discuss now. But what we see in particular, this means that B does not contain a commutative Hopf subalgebra of prime index. The prime would be 2 here, of course. And the only Hopf algebra of index 10 is of index 2 is this N, which is has dimension 16 and is not commutative. So this is not the case, and therefore it is not fit into the framework that Genia has discussed in her previous papers. Now it happens that N also arises as the unique 16-dimensional quotient of B. And the quotient map happens to be co-normal. And this means that B fits in exactly one extension of the following type in the middle where U is two-dimensional and the quotient is now 16-dimensional. You see this? And it's also this unique 16-dimensional quotient, not only the unique 16-dimensional of subalgebra. This extension, of course, is also not abelian because this is not commutative and co-commutative. But as I said, you can, so these two extensions are not abelian, but you can construct B as an abelian extension. Here's how it goes. So B has 3 sub-Hopf algebras of dimension 8, which we denote by M1, M2, and M3 because we are not very creative. Yeah. So M1 is just the span of the group-like elements. There are 8 group-like elements. The other 2 are isomorphic to the dual group ring of the dihedral group of order 8. Of these 3, M1, M2, M3, only one is normal, namely M2. And this means that B fits into exactly one extension of the type MBQ, where M is 8-dimensional and the corresponding quotient, here denoted by Q, must therefore be 4-dimensional. In this case, M, which is this M2, because it's the only normal Hopf subalgebra there, is isomorphic, as I said, to the dual group ring of the dihedral group, while the quotient is isomorphic to the group ring of the Klein 4 group. This extension is abelian, as you can say, but in contrast to the other constructions in Genia's papers, this extension is neither central nor co-central. So her extensions were usually co-central. And this is not the only way to construct it as an abelian extension. The Hopf algebra has 7 sub-Hopf subalgebras of dimension 4. Only one of them is normal, and therefore B fits into exactly one extension of the type PBF. B is in the middle as always, where the dimension of B is 4. This is the unique normal Hopf subalgebra here, and the quotient F must therefore be 8-dimensional. In this case, P is isomorphic. This is, I will mention in a second, B is self-dual, so this is exactly the dual extension of the thing that you had before. Accordingly, P is again the dual grouping of the Klein 4 group, which is self-dual, and F is the dual of the thing that we had before. In other words, the group ring of the dihedral group of order 8 now. This extension is, of course, abelian, but as before, because it's in a sense the one that is dual to the previous one, it is neither cocentral nor central. Okay, so then, of course, we have a byproduct. In the second example, we can do this too. Of course, as yet the Drinfeld Hopf algebras, these guys are not isomorphic because A was commutative and A prime was not commutative. So they cannot be isomorphic from this perspective. However, if we form the corresponding Redford byproduct with A prime, then we get something which is isomorphic to B. And this is being presented at this is covered at the end of the second paper that I mentioned in the references. Here's how the isomorphism looks. It goes from B prime to B. I hope you forgive me. This is a little bit easier to write it down then. All the generators are basically mapped in the same way, except that V prime is mapped to V times R in A. So this is very easy to, once you know the formula, it's very easy to verify that this is an isomorphism. As I said already, there is a self-duality going on here, as you can already conjecture from the way how I presented the Hopf algebras. So one of them, A prime, was not commutative. They were both co-commutative, had a basis consisting of group-like elements. So in the first example, we are commutative and co-commutative. And it turns out that this A, in contrast to A prime, is in fact self-dual in an appropriate sense. What do I mean here by self-dual? Well, if you have A star, it is not so, if you have A, it's not so clear how you turn A star into, you get the Drinfeld Hopf algebra over H. And there's some discussion necessary for this. So you have to explain how you do this. But if you do this, it works in this case, and A turns out to be appropriate. I should say all this is new and it's not contained in the papers. Yeah. All right. So this is the latest what we have been doing. This self-duality is compatible with a certain isomorphism between H and H star. And this implies that B star, which as a byproduct would be A star tensor H star, not H here, H star, turns out under these isomorphisms that it's isomorphic to A tensor H. This is what I meant by, and this is of course B. So B is self-dual. And then there are further questions. So in fact, I have not told you, I have cheated. And the cheating was, this is not only one Drinfeld Hopf algebra, there are 4 Drinfeld Hopf algebras, because you can choose one of the 4 roots of unity. All this depends on zeta. And if you choose a different zeta, you get a different root of unity. So I now need to put this in because I want to discuss this point. So I will denote A by A zeta. And then it turns out that, in fact, we get different Drinfeld Hopf algebras if we pick different roots of unity. So if Xi is a different root of unity, then these algebras, these Drinfeld Hopf algebras are not isomorphic. However, it turns out that B zeta is always isomorphic to B negative zeta. So these 4 Drinfeld Hopf algebras give only two different byproducts, so to speak. From the 4 isomorphism classes, we go to 2 isomorphism classes. Could in principle still be that B iota is isomorphic to B1, but this is what is not happening, and this is not easy to see. It took us quite a while. If zeta is a primitive 4th root of unity and Xi is not a primitive 4th root of unity, then the 2 byproducts are not isomorphic, so we get 2 different isomorphism classes of Hopf algebras of dimension 32 here. So this was not clear to us at the beginning, but this is the end of the talk. And Julia, I would like to emphasize that I did not run over, and Moniki, I did not run over. Yeah, okay. Thank you for your attention.